All right, I'd like to put one more video up. After working through your homework that's due at the end of this week, I decided to do one more lecture, clarify a couple things, and also do an example. So, starting with a formula we've already talked about, the number of remaining radioactive nuclei. You have a sample. Okay, start with a sample. A radium-228. Okay, it decays by alpha decay, has a half-life of about 1600 years, so radium-228. So how many radium nuclei do we have? Well, that number is N. The number of radioactive nuclei left in your sample is equal to the number you started with, and this is the formula I already showed you once, times e to the minus lambda t. Lambda is known as the decay constant, and it is equal to the natural log of 2 divided by the half-life. It's another way of expressing how long it takes for a certain nucleus to decay. Okay. Some have very short half-lives, some have very long half-lives. This one, radium-228 that I'm talking about, we'll use an example, has a sort of medium-length half-life of about 1600 years. Some of them have half-lives many times the age of the universe. Some of them have half-lives, 10 to the negative 20th seconds. So it's all over the map. But decay constant and half-life are kind of stand-ins for each other. They're two ways of saying the same thing. Two ways of saying how long it takes for a nucleus to decay. All right, so that much we've seen. Okay, there's another way of writing this first formula in terms of the half-life. Okay, and I'm not going to derive it. It's straightforward, and we kind of this is really just another way of saying it. It's this: N equals N naught times 1/2 to the n little n power. And this is really the definition of half-life, where n is the number of half-lives. So after 12 half-lives, you have n naught times 1/2 to the 12th power. That's how many you have left over. And again, I'll do an example using that in just a minute. So you have that to look forward to. Okay? We might actually turn this into 2 videos, 2 short ones. I think that's what we'll do. Okay. Okay. So after 1 half-life, you have n equals 1, and the number of nuclei you have is half of n naught. All right, the graph looks like this. I will turn this into 2 videos. All right, you start with n naught. Get a different color here. N naught looks like that. So after 1 half-life, you have n naught over 2, right? After 1 half-life, where little n is equal to 1 half-life, n equals n naught over 2, because 1/2 to the 1 is 1/2, so n naught over 2. After 2 half-lives, you're down to n naught over 4. That is 2 half-lives, and so forth. In that case, little n is equal to 2. You've gone from n naught down to n naught over 4. Little n is equal to 2. So 1/2 squared is 1/4, and so you're down to n naught over 4. Okay. So these are 2 ways of saying the same thing. One in terms of the number of half-lives, one in terms of time t. All right. So let's say that we have a sample. There's our sample of radium This is 88. Radium is any nucleus with 88 protons is radium. Radium-228. Okay. You have a sample there, and we start off with N0. Okay, we start off with N0. But as soon as we start the clock, that number starts to drop, according to this formula here, right? In this case, the half-life is 1,600 years, which seems like a long time to us, but on the half-life scale is somewhere near the middle. Okay. And so what happens is as soon as we start the clock, right, we start to have alpha decays. Radium-228 turns into, I can't remember what's 2 down from that. It goes by alpha decay, starts spitting out alphas. So what happens is you immediately start having alpha particles be emitted by this sample. And every time an alpha particle is emitted, that's one 228 radium nucleus that's decaying and becoming something else. This curve here tells you how many radium-228s you have left. Okay, that's what N is. How many of the original nucleus you have left over. Okay. And so we can ask ourselves, how many alpha particles per second do we get? Okay, that is known as the activity or decay rate. The number of decays per second. So we have a certain sample here. Start off with N0, whatever that happens to be. As soon as we start the clock, these things start to decay. How many decays do we get per second? That is the activity or decay rate given by the symbol R. And R is equal to lambda times N. That's why lambda is important. That's why lambda is important. Okay, because it converts a number of particles you have in. If you multiply by lambda, you get the number of decays per second, which is handy. Okay, that's the decay rate. And there's 2 units that are often used for decay rate. One is known as the Curie, or CI, and one is known as the becquerel, little b, little q. A Curie is defined as 3.7 times 10 to the 10th decays per second. I believe that is exactly right. 3.7 times 10 to the 10th decays per second. That is 1 Curie. A becquerel is defined as 1 decay per second. So with these definitions, we see that 1 Curie equals 3.7 times 10 to the 10th becquerels. Okay. Again, that's for a given sample. How many decays per second we get. Okay, the rate, that's the activity or decay rate. How many, in this case, of radium-228, that's how many alpha particles we get spitting out of this thing per second. Okay, next up, an example.